Hello, this is Colin Selleck of Binghamton University. This is a lecture in ME 391, Measurements and Instrumentation. Today I'm going to discuss fundamentals of measuring systems. Measurement techniques have been of immense importance ever since the start of human civilization for two reasons. First, measurements were most certainly needed to build structures, roads, and monuments. Second, measurements were first needed to regulate the transfer of goods in barter in order to ensure that exchanges were fair. The Industrial Revolution during the 19th century brought about a rapid development of new instruments and measurement techniques to satisfy the needs of industrialized production techniques. Since that time, there has been a large and rapid growth in new industrial technology. This has been particularly evident during the last part of the 20th century because of the many developments in electronics in general and computers in particular. In turn, this has required a parallel growth in new instrumentation and measurement techniques. The massive growth in the application of computers to industrial process control and monitoring tasks has greatly expanded the requirement for instruments to record, measure, and control process variables. As modern production techniques dictate working to ever tighter accuracy limits, such as economic forces to reduce production costs become severe. So the requirement for instruments to be both accurate and cheap becomes even harder to satisfy. This latter problem is at the focal point of the research and development efforts of all instrument manufacturers. In the past few years, the most cost-effective means of improving instrument accuracy has been found in many cases to be the inclusion of digital computing power within instruments themselves. These intelligent instruments therefore feature prominently in current instrument manufacturers' catalogs. This lecture will cover some fundamental aspects of measurement. First, we will look at how standard measurement units have evolved from the early units used in building and barter trade to the more exact units belonging to the imperial and metric measurement systems. We will then go on to study the major considerations in designing a measurement system. And finally, we will look at some of the main applications of measurement systems. The 7 base units are seen here. There's time, or seconds, length in meters, mass in kilogram, current in ampere, temperature in Kelvin, amount in mole, and luminosity in candela. We will look at each of these in more detail. The very first measurement units were those used in barter trade to quantify the amounts being exchanged and to establish clear rules about the relative values of different commodities. Such early systems of measurement were based on whatever was available as a measuring unit. For the purposes of measuring length, the human torso was a convenient tool and gave us units of the hand, the foot, and the cubit, as well as the others you see here, the digit, the span, the fathom, the yard. Although generally adequate for barter trade systems, such measurement units are, of course, imprecise, varying as they do from one person to the next. Therefore, there has been a progressive movement towards measurement units that are defined much more accurately. So let's talk about time, which has units of seconds. Ever since human beings have existed, we've measured time by observing the natural world, right? The flux of seasons, the dance of heavenly bodies across the sky. More than 30,000 years ago, men and women living in what's now Central Europe tracked the moon and stars by carving notches in mammoth tusks. From Stonehenge to the ancient Chinese observatory at Shanxi, many Neolithic structures were originally built to mark the midwinter solstice and celebrate the start of a new year. Some 4,000 years ago, it was the summer flooding of the Nile that signaled to ancient Egyptians that another year had passed. Shifting our gaze over centuries from celestial spheres to the smallest slivers of matter, we've become timekeepers of extraordinary precision. Today's atomic clocks, which operate by measuring the vibrations of strontium atoms as their electrons change energy levels, are so accurate that they won't lose a single second over the next 15 billion years. That's longer than the age of the universe. But for thousands of years, the Earth's rotation was our most stable timekeeper. So some history here. In the 1940s, a second was defined as 1 over 86,400 of the average period of rotation of the Earth. However, that is not constant. So in 1956, they changed it to 1 over 31 million and change of the time the Earth required to orbit the Sun in 1900. However, the quartz and atomic clocks invented during the 1930s and 1950s are even better timekeepers and showed that the Earth does not rotate steadily but actually wobbles. Now, since 1967, the definition of the second has been related to the movement of electrons in a cesium atom. The second is the duration of 9 billion and change periods of the radiation corresponding to the transition between two electron levels of the ground state of the cesium-133 atom. The atom can be pictured as a mini solar system with the heavy nucleus at the center, surrounded by electrons in a variety of orbits. The orbits correspond to different energy levels, and electrons can only move between levels when they absorb or release just the right amount of energy. This energy is absorbed or released in the form of electromagnetic radiation, the frequency of which depends upon the difference in energy between the two levels. By measuring the frequency of the electromagnetic radiation, like counting the number of pendulum swings, we can measure the passage of time. Time measurement has become a basic part of everyday life, and accuracies of the nearest minute or a few seconds are usually good enough for most human activities. But highly accurate timing plays a vital role in many other aspects of the modern world. The Global Positioning System, the GPS satellites, broadcast timing signals from onboard atomic clocks, which enable land vehicles, ships, and aircraft to know their location to within a few meters. Optical clocks are being developed, which may have accuracies of around 100 times higher than the best current microwave atomic clocks. That is equivalent to losing no more than 1 second in the age of the universe, as I said earlier. Let's move on to length, the meter. The first improved measurement unit was the unit of length, the meter, which was defined as 10 to the minus 7th times the polar quadrant of the Earth. And the polar quadrant is the distance from the North Pole to the equator, or from the South Pole to the equator. A platinum bar was made to this length, and it was established as a standard of length in the early part of the 19th century. This was superseded by a superior quality standard bar in 1889, manufactured from a platinum iridium alloy. Since that time, technological research has enabled further improvements to be made in the standard used for defining length. First, in 1960, the standard meter was redefined in terms of 1.6 and change times 10 to the 6 wavelengths of the radiation from the krypton-86 atom in the vacuum. More recently, the standard meter was redefined. More recently, in 1983, the meter was redefined yet again as the length of the path traveled by light in an interval of 1 over almost 300 millionths. This is the definition we use today, and it results in the speed of light to be exactly 299,792,458 meters per second. In a similar fashion, standard units for the measurement of other physical quantities have been defined and progressively improved over the years. In fact, in November 2018, the kilogram, ampere, kilowatt, and mole were redefined so that now all base units are defined by constant properties of nature such as the speed of light. This is important as any suitably equipped lab in the world can perform these measuring experiments. Let's move on to the mass. In 1791, a kilogram was defined as the mass of a declared volume of distilled water in vacuum at the freezing point. Over the next 100 years, this definition of mass was refined, and a number of weights were manufactured to have a mass equal to it. In 1879, Johnson Matthey and Company of London successfully cast an ingot of an alloy of platinum and iridium, which is a very stable material. The water definition was abandoned, and the platinum-iridium weight became the standard kilogram, known as the International Prototype of the Kilogram, or just K. In 1889, 40 copies of the kilogram were commissioned and distributed to the major national standards laboratories to be their primary standard. Until November of 2018, this was the definition of a kilogram, and it was the last unit that was based upon a physical artifact. Remember, another unit that was based upon a physical artifact was the meter, right? They had a rod that was a meter long. There were 40 copies around the world, but if you want to get specific about it, for someone to weigh 1 kilogram, it had to weigh exactly the same amount as the one piece of metal that was kept in Paris. And K isn't even constant. Depending upon how well guarded it is, it's subject to loss or gain of atoms over time, just like any physical object. And K actually seems to have become slightly heavier over the years due to surface contamination. It has taken so long to redefine the kilogram because researchers had to agree on the value of Planck's constant, which relates to a particle's energy compared to its frequency. So if you know the frequency, you can multiply by Planck's constant and get the energy. And it's been surprisingly hard to measure. Scientists have been trying to come up with a value for the natural constant since the 1970s. But in 2014, researchers finally reached an agreement on the Planck's constant. The new definition of mass requires the use of a Kibble balance, or watt balance. Kibble balances have some similarity to the ancient balances that compared heaps of grain or lumps of gold. A Kibble balance is an electromechanical measurement instrument that measures the weight of a test object very precisely by the strength of the electric current and voltage needed to produce a compensating force. Instead of comparing objects, Kibble balances use magnets, a coil of wire, and precise electrical monitoring equipment to tease out the relationship between electrical force and physical weight. Let's move on to current. It has units of amperes or amps. The ampere is the unit for electrical current in the SI system. It is the flow of charged electrons. Now, until November of 2018, the formal definition of the ampere is that it is the constant current which, if maintained in two straight parallel conductors of infinite length, you can see those here, they have negligible cross-section, and they're placed 1 meter apart in a vacuum. They would produce between these conductors a force equal to 2 times 10 to the minus 7 newtons. This is a rather difficult measurement to take. I mean, for one thing, we can't have infinite lengths or negligible cross-sections. And how do you measure this meter very accurately? And how do you measure this force? So in November of 2018, the ampere was defined by taking the fixed numerical value of the electric charge E to be 1.6 and change times 10 to the minus 19 amp seconds, where the second is defined in terms of the speed of light. So in this case, we need the speed, the second to be defined first. and then we can use this element. What they actually did was they set the elementary charge of electron to be this exact value, kind of like what they did with the speed of light, right? The 1 over almost 300 millionth of light year, or whatever that was. Let's move on to temperature, Kelvin. K is the unit of temperature. The accurate measurement of temperature is vital across a broad spectrum of human activities, including industrial processes such as making steel, manufacturing, monitoring, and food transport and storage, and in health and safety. In fact, almost every sector has temperature as one of the key parameters to be measured. In 1954, the unit of temperature was defined as the Kelvin and is the fraction of 1 over 273.16 of the thermodynamic temperature of the triple point of water. So the triple point of water is this point O right here, where in this phase diagram of pressure versus temperature, it's very easy to move into any of the other states. This is the unique temperature and pressure in which the three phases of water, solid, liquid, and vapor coexist in equilibrium. It is fractionally higher than the melting point, being 0.01 degrees C. From this single point, it is possible to generate a thermodynamic temperature scale using gas thermometers and radiation thermometers, which accurately obey known laws. Now, such experiments are not easy and are rarely done, but good values were established for a series of fixed points. So you can see those here. They figured out what for instance, the freezing point of gold was. It was, a little over 1,000 degrees C. So by having all of these physical things happening in a lab, you could do this. You could say, what's the boiling point of oxygen? You design an experiment to do it, and you could get the measurement. And that would accurately be the temperature. I mean, it's out to six significant figures. These were incorporated into the international temperature scale so that standard platinum resistance thermometers and radiation thermometers could be calibrated with excellent reproducibility. But again, in November 2018, the Kelvin was redefined using a more experimentally rigorous methodology. In particular, Boltzmann constant was defined to be the exact value of 1.38 and change times 10 to the minus 23 joules per Kelvin. The Boltzmann constant is a physical constant relating to the average kinetic energy of particles in a gas with the temperature of the gas. A definition of the Kelvin that uses the value of Boltzmann constant makes it possible to design thermometers to suit temperature ranges of interest without being compromised by the need to function well at the triple point of water. The new Kelvin definition in particular enables all equations of state that include temperature to be used to make traceable temperature measurements. From a scientific point of view, the main advantage is that this will allow measurements at very low and very high temperatures to be made more accurately, as the techniques used depend upon the Boltzmann constant. It also has the philosophical advantage of being independent of any particular substance. The advantage of this is that the new definition will be freed from any physical artifact, for instance, the triple point of water, and allow the use of any appropriate thermodynamic method for temperature measurement. Let's move on to the mole, which is the amount of substance. You may remember this from chemistry. The mole is the unit of measurement for an amount of substance in the SI system of units. Its name derives from the Latin mole or mole, whatever it means, massive amount. The mole is widely used in chemistry as a convenient way to express amounts of reactants and products of chemical reactions. The mole may also be used to represent the number of atoms, ions, or other entities in a given sample of a substance. The mole is used to describe a practical quantity of material and is the link between the microscopic and macroscopic worlds, used to scale phenomenon from the atomic up to the relevant sizes. Until November of 2018, the mole was defined as the number of atoms in 12 grams of carbon-12. Effective in, new definition as of November 2018, the mole is defined as the amount of a chemical substance that contains exactly 6.022 and change times 10 to the 23rd. You may recognize that as Avogadro's number. The new definition is advantageous in that it doesn't require the definition of the kilogram. Now we'll move on to the last unit, which is the candela, which is a measure of luminosity. The efficiency and ease with which we see things depends upon the amount of light present. It's therefore important to develop a scientific system to measure light systems. The candela is the base unit within the SI system that is used for such a measurement of light. The current definition of the candela was made in 1979 in terms of the watt at only one wavelength of light. It is defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of the frequency 540 times 10 to the 12 hertz, and that has a radiant intensity in that direction of 1 over 683 watts per steradian, which is a unit of a solid angle. Now, I don't expect you to know all these numbers, that I just threw out at you. I'm not going to ask you about how many counts of the cesium atom creates a second, and that's ridiculous. But I will be asking questions about units in general. Now let's move on to measurement system design. In this section, we will look at the main considerations in designing a measurement system. First, we will learn that a measurement system usually consists of several separate components, although only one component might be involved for some very simple measurement task. We will then go on to look at how measuring instruments and systems are chosen to satisfy the requirements of particular measurement situations. Now, a measuring system exists to provide information about the physical value of some variable being measured. In simple cases, the system can consist of only a single unit that gives an output reading or signal according to the magnitude of the unknown variable applied to it. However, in more complex measurement situations, a measuring system consists of several separate elements, as seen here. These components might be contained within one or more boxes, and the boxes holding individual measuring elements might be either close together or physically separate. The term measuring instrument is commonly used to describe a measuring system, whether it contains only one or many elements, and this term will be widely used in this course. The first element in any measuring system is the primary sensor, or it's also known as a transducer, that gives an output that is a function of the measurand. Now, the measurand is what you're measuring, so strain, temperature, length, mass. The transducer will take this input stimulus and change it into something else that usually an electrical signal or something like that we can measure. For most, but not all systems, the function that is the output of the transducer to the input of the transducer is linear. Some examples of primary sensors are liquid and glass thermometer, thermocouple, and a strain gauge. In the case of the liquid and glass thermometer, the output reading is given in terms of the level of the liquid. And so this particular primary sensor is also a complete measurement system in itself. However, in general, the primary sensor is only part of a measurement system. The types of primary sensors available for measuring a wide range of physical quantities will be discussed later in this course. Intelligent instruments also may have one or more secondary sensors. For instance, the thermocouple DAC that you used, a thermocouple can only measure the difference in temperature between the two ends of the thermocouple, right? So how do you get the absolute temperature? Well, that DAC has a secondary sensor, has a thermistor inside that measures the ambient temperature and adds it to the output from the thermocouple to give you an absolute value. These measure the environmental conditions, such as temperature and pressure, surrounding a measurement system in order to correct the output of primary sensors affected by the environmental conditions. For example, a sensor measuring temperature might be affected by the pressure in the room. So a pressure sensor is used to correct the temperature sensor. Variable conversion elements are needed where the output variable of a primary transducer is in an inconvenient form and has to be converted to a more convenient form. For instance, the displacement measuring strain gauge has an output in the form of a varying resistance. The resistance change cannot be easily measured, and so it is converted to a change in voltage by a bridge circuit, excuse me, which is the typical example of a variable conversion element, which you see here. In some cases, the primary sensor and variable conversion element are combined, and the combination is known as a transducer. Now, signal processing systems exist to improve the quality of the output of a measurement system in some way. Excuse me. However, signal processing is not a magic cure for the problems that result from poor measurement system design. Hence, it is important that the measurement system is designed properly, such that the output from measurement sensors is of an appropriate amplitude and is as free from noise contamination as possible. This is the necessary starting point for signal processing to be able to further improve the quality of the measurement system output. The electronic amplifier is a very common type of signal processing element. It's used to amplify low amplitude outputs from the primary transducer or variable conversion element, thus improving the sensitivity and the resolution of the measurement. For instance, amplification is needed for thermocouples, which have a typical output of only a few millivolts. Other types of signal processing are those that filter out induced noise, maybe a high-pass filter, or low-pass filter, or a bandpass filter. Now, in addition to these three components, sensor, variable conversion element, and signal processing just mentioned, some measurement systems have one or two other components. First, to transmit the signal to some remote point, as you can see here, some signal transmission. Think about the Perseverance rover on Mars. The signals that it gathers are sent a long way back to Earth, right? And the second thing they can do is display the output or feed the output into some control process. Signal transmission is needed when the observer or application point of the output of a measurement system is some distance away from the site of the primary transducer. Sometimes this separation is made solely for purposes of convenience, but more often it follows from the physical inaccessibility or environmental unsuitability of the site of the primary transducer for mounting the signal presentation recording unit. The signal transmission element has traditionally consisted of an electrical cable, which is often chosen to minimize signal corruption by induced electrical noise. However, fiber optic cables are being used in ever-increasing numbers in modern installations, in part because of their low transmission loss and imperviousness to the effects of electrical and magnetic fields. The final optional element in the measurement system is where the measured signal is utilized. In some cases, this element is omitted altogether because the measurement system is used as some part of an automatic control scheme, and the transmitted signal is fed directly into the control system. In other cases, this element in the measurement system takes the form either of a signal presentation unit or a signal recording unit. Choosing appropriate measurement instruments. The starting point in choosing the most suitable instrument to use for measurement of a particular quantity in a manufacturing plant or other system is the specification of the instrument characteristics required. This is especially true for parameters like the desired measurement accuracy, resolution, sensitivity, and dynamic performance. We will cover each of these in more detail in a future lecture. It is also essential to know the environmental conditions that the instrument will be subjected to, as some conditions will immediately either eliminate the possibility of using certain types of instruments, or else will create a requirement for expensive protection of the instrument. For example, measuring high temperatures or temperatures of corrosive substances. It should also be noted that protection requires the performance of that reduces the performance of some instruments, especially in terms of their dynamic characteristics. For instance, sheaths protecting thermocouples and resistance thermometers reduce the speed of their response. As far as possible, measurement systems and instruments should be chosen that are as insensitive as possible to the operating environment, although this requirement is often difficult to meet because of cost and other performance considerations. Cost is very strongly correlated with the performance of an instrument. Increasing the accuracy or resolution of an instrument, for example, can only be done at a penalty of increasing its manufacturing costs. Instrument choice, therefore, proceeds by specifying the minimum characteristics required by a measurement situation, and then searching manufacturers' catalogs to find an instrument whose characteristics match those required. To select an instrument with characteristics superior to those required would only mean paying more than necessary for a level of performance greater than that needed. As well as purchase costs, other important factors in the assessment exercise are instrument durability and the maintenance requirements. The projected life of instruments often depends on the conditions in that the instrument will have to operate. Maintenance requirements must also be taken into account, as they also have cost implications. To summarize, therefore, instrument choice is a compromise between performance characteristics, ruggedness and durability, maintenance requirements, and purchase costs. Some applications of measurement systems. Today, the techniques of measurement are of immense importance in most facets of human civilization. Present-day applications of measuring instruments can be classified into three major areas. The first of these is their use in regulating trade, applying instruments that measure physical quantities such as length, volume, and mass in terms of the standard units. The second application of measuring instruments is in monitoring functions. These provide information that enables human beings to take some prescribed action accordingly. For instance, the gardener uses a thermometer to determine whether he or she should turn on the heat in the greenhouse or open the windows if it's too hot. While there are many uses of instrumentation in our normal domestic lives, the majority of monitoring functions exist to provide the information necessary to allow a human being to control some industrial operation or process. The third application area of measurement systems is its use as part of an automatic control system. Here's a functional block diagram of a simple temperature control system in which the temperature, T sub A, of a room is maintained at some reference variable T sub D. So T sub A is the actual temperature of the room, and T sub D is the desired temperature of the room. The variable of the control, the value of the control variable as determined by a temperature measurement device is compared with the reference value here. And the difference, TD minus TA, is applied as an error signal to the heater. The heater then modifies the temperature until T sub A is equal to T sub D. The characteristics of the measuring instruments used in any feedback control system are of fundamental importance to the quality of control achieved. The accuracy and resolution with which an output variable of a process is controlled can never be greater than the accuracy and resolution of the measuring instrument used. So in summary, this lecture has covered some fundamental aspects of measurement systems. First, we looked at the importance of having standard measurement units and how they have evolved into the imperial and metric systems and units. We then went on to look at the main aspects of a measurement system, and in particular what the main components in a measurement system are and how these are chosen for particular measurement applications. Finally, we have had a brief look at the range of application of measurement systems. Okay, that's it for this lecture. See you in cyberspace.